Imagine you're watching your favorite TV show. You're at the best part of the episode, and then suddenly, frames start dropping, you get pixel distortion, and the audio and video desync. Today, we'll be learning about the component used to make sure this doesn't happen, a FIFO, and build one on hardware. Welcome to the world of digital design. This is Metastable. So, what is a FIFO? A FIFO, first in, first out, at its core, is a buffer used to temporarily store data when other parts of a design aren't ready to process it. As the name suggests, the data first written to the FIFO will also be read out first. This is similar to a line or queue at a grocery store. The first person to enter is the first to be helped. FIFOs are flexible and can be sized to fit the needs of a design. FIFO depth, or number of internal elements, is chosen by the designer, with powers of 2 being a common choice for simplicity in implementation. FIFOs work through read and write operations, which can occur simultaneously. To ensure correct operation, FIFOs also provide status flags, such as empty and full, which prevent reading when no data is available or writing when the buffer is already full. FIFOs and data buffers exist in almost all digital systems. We can find FIFOs being used in things like hard drives, GPUs, and audio and video processing, just to list a few. With an understanding of FIFOs, let's build one in hardware. So, how can we implement a practical FIFO on our Basis 3 board? One way is the following. We'll use the first 14 switches on our board to select a number in binary, with the corresponding LEDs showing the value. The last two LEDs will indicate whether the FIFO is empty or full. When we press a button, this binary value is added to the FIFO. The FIFO will store up to 8 elements. And when a second button is pressed, the next available value is read out. This value is then displayed on the 7-segment display. We'll also have a third button for reset, but that should be enough to create a working FIFO on hardware. Now you might be thinking, okay, this is great and all, but how does an 8-element FIFO benefit me? And fair enough, pushing binary values into an 8-element FIFO isn't a powerful system on its own, but it is one of the building blocks for future projects you might end up creating. In a real system, your FIFO might be thousands of elements deep. For example, instead of input from a set of switches, an actual input could be an audio processor data stream, which our FIFO would then output to a DAC, or digital to analog converter, in preparation to play the data on speakers. The purpose of these lessons is to try and teach the basics of digital design so that down the road you can tackle your own interesting projects. Even though our FIFO is humble, it'll have the features you'd need to use in a professional design. For this project, we'll end up using 5 files: a button debouncer, a 7-segment display driver, the FIFO itself, a top file to implement all the previously mentioned logic, and a constraint file to tie our design to hardware. First, we'll copy over the button debouncer file from the previous video. There will be a link to the previous video, which I highly recommend watching if you haven't already, as this video relies on previously written code. Next, we'll create a new file called seg_driver, and copy over the button counter file code from the last video as well. We'll still drive our 7-segment display, but we'll remove the button counting functionality. We'll first rename our design and then add the numeric standard package. We'll also add an input port data in. We'll remove button in, button last, and button db, and change button count array and button count to value array and value respectively. We'll also remove the debouncer and tweak our counter process to saturate all values over 9,999 for our display. With these changes, our design takes in data in and displays it on the 7-segment display. This should be all the code we need from the previous video. From here, we can start building the FIFO itself, FIFO.VHD. We'll add the basic IEEE library and packages. Before adding our ports, we're going to add a new structure, generics, to our design. Generics work like input constants. They allow us to parameterize specific parts of our design. For example, if we wanted to implement multiple FIFOs of different depths in a single design without generics, we'd have to create multiple files with a single line of code difference, which is annoying and inconvenient. With generics, We simply pass in a constant value, which is then used to set up that specific block instance, allowing us to implement multiple instances with different values. Even with just one instance, scaling our design becomes incredibly easy as our values change automatically instead of having to manually be adjusted. For our FIFO, we're going to parameterize two options: the FIFO depth and data width. We can add generics by writing the name, data type, and then the default value. If a value isn't passed in for a generic, it acts like a regular constant. If a generic doesn't have a default value, then we'll need to map a new one to it. We'll go over generic mapping later on in the video. For our port list, we have 8 ports: clock and reset, which are both standard logic inputs; write enable, a standard logic input that lets our FIFO know that we're ready to write data; and then the write data itself, which is a 14-bit standard logic vector, from data width, which is 14, minus 1, down to 0. A width of 14 gives us enough bits to represent values up to 9,999 on our display. Then we have the read enable and read data, which are the same as the right side ports, just with read data as an output. Finally, we have 2 output flags: full and empty. Moving on to the architecture, the first thing we'll need to do is create the memory we need for our 8-element FIFO. For this, we'll need a new type called mem, which is an array from 0 to FIFO depth minus 1 of standard logic vector data width minus 1 down to 0. We'll create a signal buffer or buff, type mem, and initialize all addresses of the FIFO to 0 by using a nested others set to 0 assignment, since we have 2 dimensions of data to initialize. Now we have a buffer with 8 memory addresses capable of holding 8 pieces of data. To access this data, we'll need pointers, specifically a read and a write pointer, both being integers from 0 to FIFO depth minus 1 and set to 0. We'll also add a count signal to see if our FIFO is full or empty, with a range from 0 to FIFO depth, initialized at 0. Now you might be wondering why a counter is 0 to FIFO depth while our pointers are 0 to FIFO depth minus 1. The reason is that for a memory pointer, 0 is a valid address, so 0 to 7 gives us 8 addresses, whereas the counter uses 0 to represent empty and 8 represents completely full. We'll also include full and empty port mirror signals. We use internal signals for full and empty so we can check their status inside the design. Reading output ports within a design is only supported in newer versions of VHDL. Since not all tools use these newer versions, we include internals to keep our design more portable. From here, we'll create a clocked process. We'll have reset conditions where our pointers, counter, buffer, and read data are set back to 0. It's common practice to reset all signals and outputs that get assigned in the process to 0. The reason we don't reset full, empty, or their internal signals is because they will be assigned outside of the process. Next, we'll handle write transactions. We'll check for a write enable and make sure the FIFO isn't full. If these conditions are met, we write the data into the buffer at the pointer address. We'll then increase the write pointer by 1 and wrap around back to 0 if we've hit the max address. We wrap back to 0 because our memory is circular. This means that no matter our current address, as long as the FIFO isn't full, we'll have a new address next clock cycle. The read section works almost identically to the write section, except we use the corresponding read signals and check for an empty flag instead of full. We'll also assign our output to the buffer at the read pointer address. For both read and write, as long as we have the corresponding enable strobe and conditions met, our transactions will take place, with the results ready at the next clock cycle. Next, we'll create the logic for updating a counter. The logic here is simple. If we write to the FIFO, we increase the counter, and if we read from it, we decrease the counter. The conditions here check that we have both a valid write and no read for an increase, and a valid read and no write for a decrease. In the case that we try to read and write on the same clock cycle, the count will remain the same. Now we'll move outside of the process for the finishing touches. Our internal full signal will output a 1 if our count reaches the max, and 0 if not. We'll do the same for the internal empty value when the counter is 0. You might notice that we're assigning the full and empty outputs outside of our clocked process. It might look asynchronous since there's no clock in that assignment, but these signals only change when the synchronous counter changes, which makes them okay to use. Next, we'll assign our internal signals to their output ports. We can now add a top file to implement and connect all the logic we've created. At this point, adding the IEEE library and packages should be second nature. For the input ports, we have our clock, reset, basis 3 switches from 13 down to 0, and our read and write buttons. The outputs will be our LEDs and the ports associated with the 7-segment display. From here, we'll need to add some signals. We'll create debounced read and write button push signals, as well as signals for the button levels during the previous clock cycle. Next, we'll create the FIFO signals. These are write enable, read data, full, and empty. Now in the design logic, we'll implement a debouncer for both our read and write buttons. In addition, we'll create a process that tracks the previous value of the debounced button inputs. We can use these previous signals to find out when our buttons transition. Next, we'll assign our read and write FIFO enable signals. They'll be set to our debounced button outputs, ANDed with the inverted previous value. This makes sure that our read and write enable signals only go high if our debounced output is currently high and wasn't high last clock cycle. Next, we'll add our FIFO block. We'll connect all the necessary ports with the switch value as the input for the write data. Then, we'll add our 7-segment display driver block. Read data will be connected to the data import. After that, we just need to hook up our LEDs. We'll assign the LEDs 13 down to 0 to our switch values. LED 14 will be our full flag, and LED 15 will be our empty flag. From here, we can move on to the constraint file. We'll copy down a fresh basis 3 constraint file and uncomment the clock properties, switches 0 through 13, all LEDs, all 7-segment display components, and the center, left, and right buttons, which we'll rename read, write, and reset respectively. After adding our files to a new Vivado project and building it, this is what we get. LED 15 is on, indicating that our FIFO is empty, and our 7-segment display shows zeros. To test it, let's write powers of 2. With 8 elements, our first value should be 2 to the 0, or 1, with the last value being 2 to the 7, or 128. Now, we'll flip the first switch and press the write button to load the value into the FIFO. You should see that the empty flag is no longer active, meaning we have data in the FIFO. Now, we'll repeat this process for each preceding power of 2. After creating 8 values and loading them onto the FIFO, we should see the full flag light up. Now when we press the read button, we should be able to read out all of the data we've loaded into the FIFO. That looks correct to me. Our empty flag is now high again. If we press reset, our display goes back to all zeros, and we remain empty. But that right there is a working FIFO. I'd like to do one more small test to show the power of generics with our design. Let's add a constant FIFO depth of 16 to our top file. We'll then add a generic map to our FIFO instance, which allows us to set the generic values for our entity. We'll plug in our constant value into the generic map. Notably, generic maps don't have semicolons at the end like port maps. Now the really cool thing about this is we can now change a single constant in the top file and everything in our FIFO design will scale perfectly. We won't be adding data width since we're already using the default value defined in the FIFO file. Now let's run this new design. When we do, we'll see that our design is the same as before with a new FIFO depth. We can now load 16 elements into our FIFO. This happens because values passed in overwrite the default values set in the file. This makes generics a real design game changer. But with that, you've learned how to successfully build a FIFO and use generics. That's all for this video. In the next one, we'll create a UART system and communicate with a computer terminal. Leave a like if you enjoyed the video and subscribe to stay up to date. See you in the next one.